Kia ora, I'm Mestel, a PhD researcher at University of Wellington in Aotearoa New Zealand, using seismological methods to learn about Taupō volcano and the interactions between its magma reservoir and the regional tectonics that lead to unrest and possible eruption. Taupō volcano lies beneath Lake Taupo in central North Island, New Zealand, predominantly formed during Aotearoa, the world's most recent supereruption, about 25,500 years ago. Taupo has erupted 28 times since Aotearoa, most recently 1800 years ago, and continues to display signs of unrest, with surface deformation and seismicity across the area. In addition to the hazard that a potential future eruption might pose, periods of elevated unrest at Taupo happen on a roughly decadal timescale, usually following one of two main patterns, either north of the lake, in the Taupo fault belt, as happened in 2001 on the left here, or in the middle of the lake, as in 2019. We observe different types of seismicity at Taupo, some clearly tectonic, aligning with known faults in the region, some which seems to be linked to the volcano and fluid movement. Some of the seismicity is a mix of the two. These magmatic and tectonic interactions at Taupo are a focus of ongoing research. The earthquakes and surface deformation associated with unrest at Taupo can cause significant damage and local anxiety, and I've included some photos here of the effects of previous unrest at Taupo. Earthquake patterns during the 2019 unrest episode, measured with the National GeoNet network, have been used to infer the location and size of the modern magma reservoir, which also coincides with the likely location of the magma reservoir constrained from studies of past eruptive products to calculate vent locations and magma storage depths. It also matches some geophysical measurements like gravity and broad-scale tomography which have been undertaken. However, the location and extent of the magma reservoir has not been directly imaged, so as part of the research, I will be using ambient noise surface wave tomography to directly image the magma reservoir, as well as characterizing the seismicity in the area in detail. To allow for this detailed research, we've deployed a temporary network of 13 broadband seismometers to complement the existing national network. This approximately doubles the number of seismometers within 10 kilometers of the lake edge. During the deployment of the network, we focused on co-production or co-creation of the research. We work with local people offering discussions about our research. This includes people from civil defence, emergency management and national geohazard monitoring. But more importantly, I also work with local researchers from the iwi, indigenous Maori tribes, to discuss, make connections, find agreement on site locations, and to communicate our results. As I mentioned, we're using the data both for ambient noise tomography and to investigate the earthquakes. The advantage of ambient noise tomography over conventional earthquake tomography is that it doesn't rely on imperfectly known sources, the earthquakes, which aren't evenly distributed in space and time. Instead, we use cross-correlations of background noise to retrieve surface waves for use in tomographic conversions. We pre-process the data to improve the correlations, in particular to remove earthquake signals, and then we calculate noise cross-correlation functions in 30-minute windows that are then stacked to improve the signal-to-noise ratio. For this, we're using the software MS Noise. The cross-correlation functions between the ECLIPSE stations for about 2 years of data you can see in this figure here. At the moment, this is just 66 station pairs, but we'll be including the GeoNet stations in the analysis as well, so we'll have lots more station pairs to include. We're now exploring different options for frequency time analysis to calculate surface wave dispersion and tomographic inversions to produce a 3D model. To characterize the seismicity in the region, we're using automatic picking software, EQ Transformer, to pick and identify the phases, and then Phase PAPI within the EasyQuake package to associate the picks into events. In test runs on 2 years of data, we've identified around 10,000 earthquakes. Here I'm comparing the results of this automatic picking to manual picking for a test case, a swarm of earthquakes that happened under the lake on the 9th of December 2020. This is one earthquake in the swarm, the waveforms for it, with the P and S picks marked in red for manual picks and in blue for the automatic picks. The manual and automatic picks are generally in good agreement for the whole swarm, but there are some outliers which will require careful investigation. While the accuracy and speed of automatic picking are good, we do lose completeness. Here I'm showing manual and automatic picked events for that day in red and blue again. We identified about 2.5 times more earthquakes when picking manually to the automatic picking. Here we're using non-lin-lock to locate the earthquakes with a 1D velocity model derived from an active source line across the Taupo fault belt to the north of the lake. This model is a good starting point, but we're also inverting for a local 1D velocity model using earthquakes and the Fortran program VELEST. Once the earthquakes are well located, we'll also calculate relative relocations, magnitudes, and first motion polarity focal mechanisms where they're possible. This research is still a work in progress, and in the next year we'll be running tomographic inversions from surface waves, fully characterizing and interpreting the background seismicity at Taupo. The results of these analyses and comparisons from those results to other volcanoes will enable us to improve our understanding and interpretation of the ongoing background unrest at Taupo, as well as the periods of elevated unrest and potential eruption in the future. We'll also be reflecting on our unusual co-production approach to geophysical research and network deployment. We're organising discussions with people within the project, as well as those who we have built relationships with outside. We aim to document what we've planned, what we did, and also to discuss and reflect on what could be improved in the future. For more information about the project at VMSG 2022, I've got a poster, and I'd be delighted to chat to anyone who's interested in my work. My contact details are listed at the bottom of the slide here. Thanks very much.